All right. There was let's keep going. The last question I asked in the first lecture was, can network topology, learning rate, and mini batch size be absorbed in the definition of learning activation or boundary dynamics? And we kind of discussed a little bit about it, talked about it over chat, but let's just have it written down so that if there are any questions, we can address them now. And then we'll move to the next lecture where we'll actually discuss more these three types of dynamics: learning, activation, and boundary. So the first point was, yeah, I mean, network topology is important, if not the most important thing in neural networks. Yet, with our definition of this neural set tuple, its W is just a weight matrix. Yes, some of its values, some of these elements can be zero. Some of them can be dynamical, others are not dynamical, but at the end of the day, it's just a matrix. And so you can always observe it there. The discussion we had in chat was actually important. So if you haven't followed it or understood it, make sure you do, because it would be essential for what we're going to do next. We argued there is just one weight matrix and everything, all topology is a constraint on the weight matrix. And this is not the usual way people think about machine learning. And usually they do specify, let's say, one matrix between the first and the second layer, then the second and the third. And that complicates things more than necessary. Here we are taking this unifying framework where all of the topologies are just described by the weight matrix. So the answer for the first question, yeah, it is part of this neural set tuple. The second one, learning rate. This one is one way of thinking about it. It's actually trivial. If you look at the two equations written there, you can just observe this gamma, which is the learning rate, into the definition of H. You can carry it through. If it's not dynamical, you can just carry it through and define a new H prime, which has it. Now, of course, stochastic gradient descent is only one type of learning, very efficient. It works great, but there are others. And but all of those other things, again, we should think about as generalizations of learning dynamics. And again, we'll talk about this in more details. There is a lot more to be said and done. And this subject of learning dynamics is not closed yet, not even close to being closed. And finally, the mini batch size. This is how much do you average over before you actually shift your trainable variables. That, again, is something that defines your, as we will see, boundary dynamics. So how often do you want to update your weights of biases? And also it defines your learning dynamics, is what kind of averages do you want to do in your stochastic gradient descent. And when L is the number of layers, or L+1 to be more precise, then this combination M times L appears in both, as again, we'll see something today. And, questions can be asked, why is it the same number? Can we update boundary with one frequency and then do the learning dynamics with other frequency? And then when we discuss generalization of learning dynamics, all those things would be possible. This is an open-ended question, and there are certainly other hyperparameters, and we should always think about them. And there are actually, libraries and tools that'll tell you, okay, so you've trained your neural network, but you don't know what the most optimal hyperparameters are. Let's just train them on top of it. What it would be interesting question to address is, can you actually take all those hyperparameters and incorporate into your neural network itself? Maybe enlarging your architecture, making something more sophisticated where everything that is trained is just trainable variables, and hyperparameters would automatically train. So again, this is something we started discussing over chat when we said, all right, the number of layers may be one of those parameters. The question in the chat was that let's specify it and let's see what kind of constraints you would want to impose it. But you can also ask a question, can we train for that? Can we now, in addition to training for all the trainable variables, think about L as being just one more trainable variables that would be trained? Okay, so yeah, many questions, fewer answers, lots of open-ended projects for you to think about. The next, in this lecture, what I want to pay attention is to those three types of dynamics. And I think it's important to keep them separately, although we'll see that they interact with one another in very interesting way, non-trivial way. And here on the first slide, I just put everything together with a physicist hat on, right? So I put a physicist hat on and say, all right, in physics, we study dynamical systems. In mathematics, they also study dynamical systems, but in physics, we do that all the time. And what are the analogs of these three types of dynamics that we see in physics? And although, again, this is still not precise, this is something for you to think about, but this identifications with the physical system allows you to think about how you would go about generalizing it. Again, the idea is for us to have a unified framework, yet to see what kind of things can be generalized, enhanced, and maybe useful, maybe found to be useful. So let's start with the boundary dynamics. In boundary dynamics, we usually consider probability distributions. We'll think on the next slide, I'll show you what kind of distributions there are. But more generally, you can think about probability density functional, right? So this is a square bracket notation where the variable here is not a number, but a trajectory. And you can say, all right, so what maybe I can generalize the probability distribution of MNIST data set of images. Maybe there is some paths that I want to train for, some trajectories. If so, what would be the right framework to write down this probability distribution? How would I be streaming data to my neural network if I am to do that? Now, I call it boundary dynamics for multiple reasons. In machine learning community, people just call it training data set. One reason for that is because we'd like to think about this as something outside of the system and yet interacting with the learning system, so it is kind of at the boundary. And the other reason is dynamics is important there. Okay, so yes, I'm saying it's similar to statistical physics, and so physicists who had been dealing with statistical physics know well about probability distributions. With probability distribution over paths, it's less clear. The one thing that should ring the bell is Feynman path integral, where distributions over paths are discussed. Although the difference there is that it's not a distribution over paths, but it's a probability amplitude over paths. There is a difference for that. At some point, we'll discuss it as well. Okay, the second type of dynamics is activation dynamics. And basically, all it says, you have a state of the system and they have a way of the state being transferred to the next time. So it's a time evolution of a state, where a state is described by a state vector x. Now, here I only discuss evolution of the bulk neurons. And so the law of evolution, which is this one, is only for the ones that are inside your neural network. This is what's sometimes called hidden neurons. And then you have two different rules, right? So one rule is how the bulk neurons would evolve through the activation. And the other rule of how the boundary neurons would evolve through some kind of probability distribution or probability distribution functional. And nevertheless, they interact, right? So as you can see here, this X has no superscript /D, meaning that you need to know the entire state to figure out what is the next time step of those bulk neurons. It is very similar to classical physics, because if you look at it, all of the classical physics is like that. You have a state of the system, position and momentum in one time. You can find out what the state of the position and momentum the other time. It doesn't matter how many molecules, how many particles you have, how complicated your system is, it's always this evolution. One difference that might seem important first from classical physics is that dynamics here is discrete. You just take discrete time step. Nevertheless, you can always take limits where in classical physics, you can discretize your motion. And this is what you do when you're simulating your system. And for a machine learning system, you can take very large time scales, and then you can T can be effectively continuous for you. Now, the least understood dynamics, and again, I wouldn't be giving those lectures if it was not for that confusing dynamics. The third one, it's learning dynamics, where the rules are completely different. Now, you can still think about this as something that we've seen in physics, and I argue that this is mostly related to the gravitational physics. So think about your tabletop experiment where you may have particles or you have fields and they evolve, and there is a predetermined rule how things change. And now you start messing around with space. You can start stretching it and squeezing it and kind of changing the strength of the interactions. And that's what the matrix effectively does. So here, the analogy not exact, but it just brings you the important point that the evolution of those degrees of freedom are very, very much different. Now, in the previous lecture and going forward, I'll be calling the variables that evolve according to these dynamics, I'll be calling them trainable variables, as opposed to the first two dynamics, which describe the evolution of non-trainable variables. The key equation here is stochastic gradient descent, but as I already said, this isn't written in stone. You can try to modify it. You can introduce momentum. You can introduce Newtonian method, and you can change it for gradient descent as opposed to the stochastic gradient descent. And all of those things may be important for certain applications, but as the number of degrees of freedom becomes large, you have to go with the fastest there is, and stochastic seems to be the one. Okay, so are there any questions about this general setup? Because every time now we're going to discuss something, and let's say you're proposing, I want to modify, do this, or I want to investigate that. My immediate question will be, what are you trying to research on? Are you trying to think about the boundary dynamics? Are you trying to think about activation dynamics, modifying it, or learning dynamics? And that would be the question. And then you'll say, well, maybe all three. I say yes, but as a physicist, let's make this approach of, toy model approach. Let's do one thing at a time. Let's first think, for example, boundary dynamics, and then figure out what is it exactly you want to do with that. And once you're absolutely sure you know what you're doing there, then you may say, okay, now I want to generalize activation dynamics, and we go from there. Let's not try to do everything at once, but break it into small pieces, small progressive steps. And so keeping in mind those three types of dynamics are useful. Now, it happens so if you write it as LAB in the learning activation B order, looks like a lab. This is just coincident. I had no intention of doing that first, but yes, if you think about this, it is a kind of a lab dynamics that we are machine learning lab dynamics that we are investigating here. Okay, any questions about the general setup? And then the plan of the lectures today is to go through all those three dynamics and seeing, how they're different, what can we do that, how can we generalize them, etc. And of course, the rule is if you have a question, just speak up. Don't have to raise your hand. Okay, so let's start with the boundary dynamics. This is what you usually have. You have a probability distribution over a finite collection of time-independent states of boundary neurons. It is a sum of delta functions. You can normalize it. It's not a big deal. XM here parameterizes those samples. Each XM can be, for example, handwritten image of a digit like a MNIST dataset or something else. And then you just add them up. This is your probability distribution, and say, well, neural network, learn it. And then that may be your task. Now, more generally, you can have a probability distribution. We usually in physics like to take a log of the probability distribution, and then the probability distribution expressed as an exponent of something. And that something can be anything at all. The simplest non-trivial example where your distributions would actually be normalizable if that something is a quadratic function, and then the distribution is Gaussian distribution. Of course, you can have arbitrary functions here. You can add a quartic term, cubic term if you have a quartic term, but at the end of the day, anything you enter there, whatever distributions you're trying to study, whether it has one minima or many minima, the point is for you to have it normalizable. Now, one important point I'd like to emphasize, because it will come around many times, is that the X sub D here, the boundary neurons contain both input and output neurons. So if you are thinking about some kind of classification task, about labeled data, it has everything. It has everything there is. Now, it is your choice to decide to treat them separately when you connect this boundary to the bulk neurons. But that choice is not written in stone. And there are papers trying to move things around, and you may want to do that as well and see the effect of that. But your training data set comes with just collection of data where there need not be any difference between input and output, unless you want it. Okay, so so far it's simple. You sometimes have that. Maybe you have a model like this. Maybe you have some physical system that generates infinite amount of non-repeated data from you, and you're just trying to model that. Then there is some underlying probability distribution. You may not even know what the K is, but nevertheless, your training neural network just reproduce exactly that K. Now let's complicate it a little bit more. And this complication is not something that I just cook up. This is something that actually useful. Useful even if your training data has no temporal dynamics, has no time dependence, has no ordering. Sometimes it turns out to be useful to have them, to have this ordering. Useful in a sense of it doing something better. It makes the network learn better. Now, what do I mean by neural network to learn better will be more explained more explicitly when we discuss learning dynamics. Okay, so this is the first non-trivial complication. When you say, all right, we are still working with this discrete states, but I'm going to shake them. I'm going to shake those images. Maybe I'll introduce some kind of noise to them, and that will give me more of the training data. Or maybe I'll give them some dynamics. I will actually tell how the state of the boundary neurons will change with time. So initially, I may just choose a random image, random data, and then I will have that evolve this way. And there may be terms. Actually, they may be terms that like this first term, which penalizes changes in the boundary X. So for example, if alpha is very, very large, then all of your changes in time will be suppressed, small. And then there may be this kind of a potential term for the boundary neurons, which will tell you where their most likely values of X would be. This is similar to this term. The only difference here is dynamical. Dynamical meaning you really have to integrate, right? So now this integral takes any trajectory at all and shoot out a number. So for you draw any trajectory you like, you'll get a number out of this. You exponentiate it, and that will give you a probability of this trajectory. Some trajectories will be suppressed, others will be enhanced, and you choose what you want it to be. Now, this type of probability distribution on paths actually is generated by something that you can call a Markovian process. You can actually expand it out because you have here a summation and their exponent. So you can express it as a product of terms starting from initial conditions and going on forward. Because you have sum, and an exponent of a sum will be a product, and you have like kind of a product of transition probabilities. You can express it this way. You can think it about this way. And so it's the simplest thing you can do. Once you start adding high derivative terms here, you will see that your state doesn't just depend on the previous state, but may depend on 2 steps before, 3 steps before, and then it stops being Markovian. But that is, again, something that you may want to do. And as I said, this may be something that your data set already has, or something you make your data set to have by reordering the data. So going back to the example, let's say not going back, but new example of cats and dogs recognition, right? Let's say this is your data set. Do you want to randomly, and you have a collection of images, cats and dogs. Do you want to randomly sample cats and dogs, or do you want to first go over all cats and then over all dogs? Or maybe you have very few images of cats and dogs and you want them to move around. You want to shake them up a little bit. And that way you will get more training data. All of those things you can accomplish by this term. Now, the third one is slight deformation of the first one, where in the initial conditions, I no longer take a discrete set of initial data, but I take a distribution at zero time. And then I still multiply by this exponent, where the exponent is again something we cooked up in physics because we are trying to, and the reason why it's written this way and ordered this way is because you're trying to see if there exists this function L of those two variables that actually describes your evolution. But if you look here, there are those three dots, meaning that you can have arbitrary things going forward. You can have second derivative, third derivative, fourth derivatives. Even within this term, with only the zeros and the first derivative, you can have mixture between derivatives. Now, and you can continue doing that. The one important thing that we also discovered in physics, and we should keep in mind, is sometimes your data set has some symmetries. And then if data set has symmetries, for example, location of cat is as good here or there, it's a shift symmetry, then the probability distribution must have those symmetries as well. So, and then your hands are a little bit tied. And when you come up and cook up this function L, you have to pay attention to those symmetries. Here, it's all hidden because I don't have spatial integrations, only time integration, but yet all this can be generalized and present there as well. Okay, now here again, I add this slide with open questions. Can it be generalized further? And of course, the answer will be yes. And here are the directions for you to think about. What are the possible couplings that you can introduce between bulk and boundary neurons? Here, as you see, all this probability distribution did not depend on the bulk neurons. There was no feedback. Whatever bulk neurons are, the boundary dynamics is not sensitive to it. However, last lecture, we argued that for the at least reinforced learning, the state of the bulk neurons, the state of the neurons which neural network generated, should affect the state of the system, and therefore affect the boundary dynamics. And therefore, there has to be this feedback. That's one generalization. Other one, as I already said, this is kind of a Markov process, but you can think about non-Markovian process, how to generalize it. You can think about second order probability theories, when you have probability of different probability distributions, etc., etc., etc. All those things are only useful if you show that they're useful. Other than that, they're just directions to think for you about. Unless you can prove and show that certain modification of the dynamics is beneficial for learning. And again, I'm referencing something I'm going to say in the future, is what do I mean by neural network being efficient? What is it? What does it really mean? Can we actually have a number that is calculated and says, okay, yeah, this neural network is good, this one is bad. Okay, so I'm done with this boundary dynamics. I just opened this Pandora box. Of course, there's many directions to go, but yet let's see if there are any questions as of now.
Yes, I have a question. Are there any methods that can help us in finding the best trajectory of learning?
Yeah, well,
not learning, putting input data.
Yeah, so there was a brute force, of course, always, and just try different boundary dynamics and see which one works. And that may be the first attempt you want to do, and you should do. But then again, you should think harder about if there is within the problem already something that tells you what kind of dynamics there should be. I mentioned symmetries. So if you have certain symmetries in the system, For example, as I said, you think that location of the cat should not determine the outcome of the learning. Then maybe you should make sure that your dynamics respects that. You do not just put cats in one corner and train your neural network for that. You make sure the cat goes everywhere around. But again, something in the data or in the problem itself may suggest that there are certain symmetries. And once you have those symmetries, you put them in the boundary dynamics. And that would be like a theoretical approach, analytical approach. And then there is a brute force numerical approach to just try different things, come up with some ensemble of possible dynamics, and then see which one works better.
Yeah, instead of brute force, can we implement something like a genetic algorithm?
Again, a genetic algorithm is just, again, an algorithm, and separately from, so your question may be asking, can the system learn what is the best, it's not exactly genetic, but maybe let me rephrase it. Can the system learn what would be the best boundary dynamics? Now, my answer would be, if it can, that maybe this type of learning actually can be pushed into the bulk, okay, and then leave the boundary outside of it. So effectively, you'll be streaming data, which is a boundary dynamics, and then there'll be kind of a layer that is trainable. So do not put anything trainable within the boundary dynamics, because that's not how it is defined. Try to separate the two things. In fact, it will be one of the important, unless we prove that the mixture is important, right? So if it's important to introduce some kind of learning within the boundary dynamics, and by proving, I mean come up with a toy model where this would be explicitly illustrated. Okay, any other questions? Okay, so let's move forward. The activation dynamics. So this is the second type of dynamics that is present in neural networks. It is maybe the simplest, because we really know the rules. At first sight, it's the simplest. You just have a state, and then you see how the state evolves. Now, it only determined by the activation map. So this map kind of tells you everything there is. Mathematicians would love it, because this is a dynamical system, right? What else can it be? You know the state of the system, you know to where it will go. Seems like a perfect playground for us to apply all the dynamical system methods. We complicate it first by making it nonlinear, and the complication is essential for learning. If you make it linear map, then it isn't just not going to produce you any non-trivial results. Every deep network we would be able to collapse it into a shallow network, and everything would be easily solvable analytically. Now, so that's a complication. Now, a simplification that we do is that we are saying that it's separable, in a sense that out of all of the components of the input to this map, the respective fi only applies to respective yi. So in general, it's vector in, vector out, but we want it to act separately to each of the components. That's a simplification. Not clear whether this simplification, and actually it's more or less, we can talk about this. It's not clear whether this simplification is actually reducing the complexity of possible maps that we can discuss. Basically, we are just yes or no. So there are two ways to do it. This will be one of the questions that I'll ask. Can you actually come up with something non-trivial by removing this simplification? Now, an important property of this activation map that you can extract is to look at its matrix of first derivatives. So you have f is a vector, y is a vector. They both have components. You can differentiate fi with respect to yj. Now, the first assumption that we make that this matrix is completely diagonal, and that comes from here, right? Because it's separable. If I differentiate f1 with respect to y2, I'll get 0. But it is nonlinear, and so because it's nonlinear, you don't get identity. You actually get something that is not identity, and that's a complication. Again, those two complications, simplification, are translated into the simplification and complication of f prime of the matrix of derivatives. Now, why do I pay attention to this matrix of derivatives? It's because this is how you would go about studying stability of the dynamical system. Here is the illustration for that. So we can keep iterating. We can keep taking vector x and then plugging it back to get at time t, get at time t plus 1. We can keep all of the boundary neurons fixed so they don't change, and all of the bulk neurons are keep. We're just iterating with this activation map. What happens usually? You get to a fixed point. Now, this is there's two equations, just definition of what a fixed point is. But then you may want to ask whether this fixed point is stable or unstable. And the stability and unstability in the dynamical system literature is analyzed through the so-called Lyapunov exponents. So let's see what those Lyapunov exponents are here with respect to this system. As I already said, this f prime matrix of first derivative is important. The reason it's important, you just go to the fixed point and linearize your system around that point and see how the small perturbation around the fixed points propagate. If the Lyapunov exponents is negative, any small perturbations of x in that direction will shrink exponentially fast. And if there are any directions where Lyapunov exponent is positive, then they will expand exponentially fast. And so if all of the exponents, Lyapunov exponents, are negative, then the fixed point is completely stable. You start in the vicinity of the fixed point, and the system goes there. If one of them is positive, then yes, all of the directions may squeeze, but there'll be one where it will grow. And so the system will, the chaos will appear, and basically starting from some initial point which is close to the fixed point, you will end up in the point which is very, very far. Okay, now Lyapunov exponent is nothing but the log of the eigen values of this matrix, and this matrix is what you would get from these equations if you are trying to linearize the system and see how the small perturbation will evolve. Now, for some type of learning algorithm, it will be important for you to get to the fixed point. For others, you may actually benefit from not getting to a fixed point. So let's take an example of the layered neural network. After L steps of the activation dynamics, all of the neurons acquire the state that they want to have. You keep the input neurons, you iterate your activation map. After the first step, the signal propagates from the first layer to the second. After the second, from the second to the third, and so on. And eventually, all of the states of all neurons are fixed. And they no longer change unless I modify the input state of input neurons. And so you know for sure that for this type of dynamics, the system will be completely stable. And you can also try to calculate what kind of map that would be. You can actually take this W matrix. It will have all eigenvalues equal to 0. And you will see basically at the end what kind of dynamics you will get, right? So let me now go on and generalize it. Again, there always will be the questions, okay, here's the setup, here's what we usually have, but is this all we want? Or maybe we want to generalize it. And if we do generalize it, what would be the benefit of it? We already discussed last time complex and other fields, and so we'll not go into that. Again, there are benefits and there are problems with it. Now, the one thing I already mentioned is if this separability is violated, would that be useful in any case? Yes, it will calculate the complicate the calculations, make the problem is more computationally complex, but maybe it will come with benefits. And so something that we can discuss. There are maybe also some topological non-trivial maps. There are some kind of maps where topology plays a role. Again, something we discussed in the chat briefly. This should be investigated. Now, what about noise? So far, this is completely deterministic, right? You just have a state and then it goes, there's no noise to it. Do we need to introduce noise here? Or we can just think about noise coming from the boundary? Because remember, there was lots of stochasticity in the dynamics of the boundary. Maybe all you need is to keep this to be completely deterministic and then have stochastic noise, whatever it is, white noise, any noise you like coming from the boundary conditions. And then again, we would have accomplished the mission of separating the two types of dynamics and only using whatever essential here to the task that we do here and leave all of the probabilistic stuff to the boundary dynamics. This is also can be inverted and say, well, maybe if there is something deterministic that you want to put in the boundary dynamics, maybe you don't do it there and just leave it up to the activation dynamics to do that. And that's, again, open questions to discuss. All right, so before we move on to the third and most important dynamics, let's see if there are any questions. Okay, good. So most important, least understood, least trivial. Now, the key object in the learning dynamics is a loss function. And so here I remind you of what type of loss functions we already discussed. Now you should think about this loss function as maybe as a Lagrangian or Hamiltonian in physics. You are free to write any functions you like, but at the end of the day, you want to see whether it agrees with experiment. Now, in our case, experiment is training neural network and then seeing that actually does what we wanted to do. And so you're free to write anything you like, but at the end of the day, you have some experiment to conduct and see whether it works. Now, so the two kinetic terms, the first one is for the boundary that we always use in the classification, for example, problem. This is a mean squared error on the output layer. This is it, basically. Now, however, you can have a modification to this loss, come up with some other function and see whether this will benefit the learning or not. Now, the second one is less well known. This is a bulk loss, which resembles closely the form of this first loss. However, now we're summing over all the bulk neurons. So what does it do? It actually tells you how far away you are from the fixed point of the previous slide. So if you are at the fixed point, you are good. So the loss is small. If you are far away from the fixed point, it is large. So the motivation for this comes again from this feed-forward neural network with a layered structure, where we know that after a few steps, you reach a fixed point. Here, you do not demand how many steps it will take you to reach there. You just say, well, generally, it is beneficial. This term would ensure that you are close to the fixed point, meaning less instability, meaning all of the nearby trajectories converge, meaning that Lyapunov exponents around that fixed points are all negative. Okay, and then the potential terms. And the first one is, of course, you can write arbitrary sums here. So I wrote separate sums for x and b and w. They can be functions that combine any one of them together. The first time, for example, for the binary classifications, this is a double well potential, where it has at small values of x, it's inverted parabola, and large values, this x to the fourth term starts dominating and starts becoming fourth power polynomial going upwards. And so there'll be two minima at x equals to plus and minus 1. And so the system would want to go there. And it would say, all right, I want each neuron to classify. Whatever you do, whatever your task is, in addition to that, I know that is important for each neuron to classify. So roll into either plus or minus direction. And then the system will decide for which samples of the boundary data it will run to plus 1, for which it will roll to the minus 1. Sometimes this x to the fourth term is not even important, because there are already constraints on your activation map. So if activation map is something like hyperbolic tangent or sigmoid, x cannot be larger than +1 or -1. So you don't even need this term for, and you can only keep an inverted quadratic term, and it will already classify. Sometimes you do not know whether individual neurons will want to classify, and you first want to run your learning algorithm. You see that certain neurons start to classify. Then you understand that that's what they want to do, and then you modify your loss function to help them do that, right? So once again, I'll repeat it. You first run without this term. You discover experimentally that it turns out that there's some bulk neurons, or maybe all of them, would want to classify, and then you add this term to help them accelerate them to do better. Now, for example, in the MNIST data set, you can actually observe that. What will happen, you look at the distribution, you take one neuron and look at its distribution, and you will see that there are two peaks are developed. First, you start with a single peak, because the neuron doesn't classify, doesn't know what he's doing. But then you develop gradually two peaks, and that's when you know that the system classifies. And the peaks become narrower and narrower. Entropy of that distribution goes down, and system becomes a good system that is kind of learned what it wanted to learn. Second one is L2 regularization. It's the problem is there may be runaway solutions for W and B's. W's become very large, B's become very large, system becomes inefficient, and so maybe you want to penalize that. And so we want to have quadratic, for example, quadratic L2 time regularization for biases and weights, and that can be written as a transpose this way. For the B, you would write B transpose B. I didn't write it down, but there is always a notation which in indices and without indices. Now, this term we discussed. So we talked about L-layered architecture. For the later slides, it will be more convenient to me to call L plus Y layered architecture. So L is one less than the number of layers. So if you have 2 layers, then L is 1. If you have 3 layers, L is 2. This is just notations for the slides that follow. It has nothing, there's nothing deep in there. And we discussed that a term like this would be beneficial. Why? Well, it will make sure that their weight matrix raised to the L plus 1 power is as close to the 0 matrix as possible. That's certainly makes sense. Now, there are, of course, as we discussed in the chat, there are many other layered structure that would not be constrained for that. So, for example, having if L is equal to 10, then having L equals to 1 would work as well. So, and maybe you do not want that to happen. You want the number of layers to be exactly L, and then you have to play around with not just this term, but with the function, which is a function of these terms as a function of L. So you want to have some function of L multiplied by a term like this, and then summed over all L's. And then there will be this mega function that is kind of tells you what are the layers that are preferred, which layers are not preferred. That may not be essential. This term might just work for all practical purposes, but still something to discuss, to think about. Now, adding a larger term in front of here will make this term more pronounced, and making it small, less pronounced. The other thing you may do when you don't know how many layers you want, and you kind of there is a freedom, or you don't know how precise your layered structure want to be, you first run it and then see, because of the constraints, certain elements stop changing, don't change much. And then you just eliminate them. You prune your connections. You don't you use them for learning. And then what you effectively do, you discover the preferred architecture, right? Instead of imposing it, you dynamically discover it and then make use of it and then stay with it. Okay, so that's a general setup. Now we come to the point of actually saying, all right, what is it that we want our learning system to do? How will we be evaluating whether the neural network is good, it's bad? What is the parameter that will tell you about this? So one parameter is the average loss that is usually used. And here, as I said, I'm thinking about L plus 1 layered L plus 1 layered network. So I'm thinking that every time step in the bulk neurons change every time step. And then every L-1 time step, no, actually it has to be elf time step. So yeah. And every elf time step, I think that the boundary changes. So let's say we have a two-layered network, right? Then L is equal to 1. Then you change your bulk, you change your boundary, you change your bulk, you change your boundary. Now, if as the number of layers becomes larger, then you change your bulk and then a few times boundary, bulk, a few times boundary. And then as you keep doing that, you keep evaluating whatever your average loss is. And you get a number that will be kind of summed up over all L's and all M's. Now, this is one way of doing this. Of course, sometimes if you do have a layered structure and it takes you time for the signal to actually reach the final layer, then you have to not sum over all states of the loss function and wait until the end. However, if your output layer only changes once every L time step, then it doesn't matter. And so in this formula will still work. Okay, but that's well known, right? So we know that U depends on T. Now, what is less known is how it changes with T. It is what people usually do. They train their neural network. They get to some place where they think it's good enough. They cut it and say, okay, I have a good enough neural network that was trained well enough. Now, the few questions arise. First of all, first question that I'm not discussing here is that there is a difference between loss and accuracy. Okay. Now you're training for loss and they are checking the accuracy. That seems to be an overdone, right? So you really want to train what you are checking. The reason you don't do that is because your accuracy-like function actually has discontinuity. So if you think about this, the reason we do not train for what we want the system to do is because the system is discontinuous, and we really want the loss function to be differentiable for the back propagation. Okay, but let's remove this problem aside, and let's just say we do really want to trade for the loss, and we want to look at how this function changed, and we want to make this function as good as we want it to be. But then what does it mean for this function to be good? Well, before we answer that question, let's try to model it. What is the functional form of this U of T? And this is the model that usually works. There are exceptions when it doesn't work, but usually it does. Now, and if it doesn't work, there is a reason for that. So there is real reason for that. I think I know why. It has to do with the changing temperature that we'll discuss next time. And that's what's going to be next lecture about. There is a notion of the machine learning temperature. And if it changes, that this solution will not be very accurate. But nevertheless, for all practical purposes of a simple task, this is a good model. What does it have? It has this decaying exponential. This is what you want to decay as fast as you could. So you really want to make this alpha to be as large as possible. The larger, the better. So you are looking for a neural network that learns fast. And so we can call this alpha efficiency of learning efficient, how fast your neural network learns. You can change its shape of its architecture. You can change the learning rate. You can change different things, and then see how all those hyperparameters affect the efficiency of learning. But at the end of the day, this is your task. Okay, but maybe that's not what you want. Maybe you don't care how fast it learns, and you have plenty of time. You have weeks and weeks before the product needs to be delivered, and you only worry about the asymptotic loss. You're only worried about how good neural network will be once it learns. And then you have to pay attention to this U0. And I call it equilibrium loss. Sometimes it's called asymptotic loss, meaning this is the value of the loss that you would get in the long run. If you keep running your system for a very long time, infinite long time, what will it be? Now, and the third part is noise, the fluctuations. You may have a situation that you do really have a very large alpha. It learns very fast. You do have a very small U0 and it learns to very small values, but the system is highly unstable. So small perturbation generate huge jumps. So can you imagine you are in a self-driving car that is beautiful, like everything works great, it turns, make the turns, but then somebody shows some weird sign to it, and then it misinterprets it, and then it crashes. And so it creates a very large fluctuations just because there's some signal that came from the boundary, right? From what it's from the environment that just destroyed completely the system. So the system completely unstable. That's not good. So in those cases, you really want to pay attention to the eta, to the mean square of the fluctuations. So here's a bit of the stochastic processes here, right? So we assume that the average eta is 0, average over time. Now there is some variance to the fluctuations, but it's actually may not even be Gaussian. So you will not have this, they will not be equal to this. So I mean the noise are correlated. So for example, it gradually accumulates noise and then suddenly jumps down, or other way around. It creates a huge noise and then it slowly decays, which is really what's happening. The non-Gaussianity of this type of fluctuations that are caused by fluctuations of the trainable variables is being studied here a little bit, but it's actually a huge thing. So really seeing non-Gaussian fluctuations and seeing what they are suggest very many analogies with physics, and also how these things could be analyzed. So things like criticality, scale invariance, phase transitions, it's all about that. It's again, we are not going to discuss it now. We will get to that later, but all of the interesting non-trivial phenomena are happening for non-Gaussian system. Okay, so now, so we have this ansatz. We're trying to extract all those constants. In fact, if you instruct those constants earlier on, when the system started training, you can, ahead of time how long will it take you to train it, right? So this term becomes subdominant when alpha is 1 over t, right? Then it starts becoming subdominant. And so you can ahead of time predict what will be the general shape, and you'll say, all right, that's how much time I need to train this neural network. And then if this time the training time is beyond what you can afford, then you kill your process, and then you start reinventing the smarter architectures or constraints or a loss function that will accomplish your task better. Being able to actually model and extract those parameters are essential. Now, how you do that? Well, the good thing about this eta t is that it averages to 0. So if you smooth this function, you will get rid of that term. So if you just put some window function and smooth it out, you will get rid of the fluctuations. The other two will still be there. Now, the second good thing about this is that if you differentiate the whatever function you got with respect to t, you will get rid of u0 as well. And you will end up only with this thing. And so averaging, differentiation from t, and then getting this term brings you very close to extracting alpha and a. And the way you extract alpha and a, you just take a log of your result. And once you get a log of the result, there has to be a straight line. It has to be a straight line. So log of this function versus t has to be a straight line. If it's not, that's what I said, it's a deviation from this model, simple model. Most likely it expects that on the time interval considered your temperature, the parameter that plays the role of the temperature in statistical ensembles is changing. And then you have to work harder to extract, to come up with a different model where this even alpha changes. And so that becomes more of a mess. But that should be the plan. And then every time you develop a neural network to do something, you can ask the 3 questions. Do I want it to train fast? Do I want it to have a good asymptotic or equilibrium loss? Or do I want it to be stable? And then there is a combination of those 3 things that you would want to accomplish. And then depending on what is it that you really want, the combination may be different. Okay, so let me go on. Okay, so what do you mean combination of them? So really you looking at those 3 parameters, and then you're saying, for example, how does it change with all of the hyperparameters you have? How does it change with the mini batch? How does it change with the learning rate, number of layers, and others? And then by looking at those particular parameters, you will be able to extract what would be the best combination of those hyperparameters for you. So this is like hyper training again. The question whether this hyperparameters training can be absorbed back to the neural network, so you don't have to separately train them, is again the question I've mentioned earlier. It's an important one because ideally we don't want to train anything outside of the neural network. Neural network itself has to do all the training, and if there is any hyperparameters, think about this maybe an extra layer that you would add where all those hyperparameters would exist. Okay, but that mapping this idea of absorbing of the hyperparameters, all of them into just neural septuple is again this idea that we can try one by one, but it's not a completed and accomplished task yet. Okay, we're past our bedtime, so let me hurry up a little bit. I only have a couple of more slides, I think, yeah, and that's it. All right, so we already discussed the choice of loss function depends on learning, but it also depends on the type of a learning task. And here I just want to discuss the supervised versus non-supervised. Again, we did talk about this. Now we'd want to emphasize the main difference between the two in terms of the things we discussed today. So for the bulk loss, we have the boundary conditions that are satisfied exactly, and the fixed point equation is not satisfied exactly, so it is where all of the error is, right? So you fixed your boundary conditions, you don't change, but you allow arbitrary trajectories in the bulk to change. And that works well for the both supervised and supervised learning system because everything is defined inside of the bulk. It doesn't depend on the boundary. There are no output neurons. One example, you say, well, whatever you do, make sure that each neuron classifies. Great. So you train it, and then it classifies each neuron, start extracting some features, memorizing them, making sense out of them. For the boundary, it's other way around, and it is the fixed point equation that is satisfied exactly, this one, but the loss function is represent the mismatch in the boundary conditions between what the output neurons you want to have and what output neurons would have had if we had your activation dynamics propagated. That is fine. I would like you to think about this little problem now. This is a little problem where you, instead of insisting on the layeredness, again, number of steps, you are saying, all right, so I may never reach the equilibrium, so this equilibrium may never be established. And if it's not established, I want to activate my dynamics for a certain number of steps, or that's subset steps L, or until this deviation from the fixed point is smaller than something, the tolerance. That's something we call tolerance. So how bad is the fixed point equation is violated? So this is the combination of the two. So now, great. So you propagated your neural network for a few steps. Then you observed that your fixed point equation is violated a little bit, but maybe not too much. And so L and epsilon are satisfied. You have a definition of the loss function. And now you're saying, all right, so now I would like to backpropagate. Okay, so how do you do that exactly? So this is the less clear, because in a layered structure, you know how many steps to take, you know exactly where the loss function is sitting, you know exactly how to go back. Now here, you took the number of steps, you already, you haven't satisfied your fixed point equation exactly, you got to some state, you can still differentiate your loss function, whatever it is, with respect to the trainable variables, but what do you mean by now propagating back? Because in the former sense, back was going from the last layer to the previous, to the previous, to the previous. But now all neurons are connected. And so you have a state of all those neurons. There is a loss function defined on them. And so there is no back in a sense of going back from layer to layer, but there is still back in terms of the activation dynamics that was taken forward. So you should think about this and see how you would actually implement the back propagation here. And that would apply to this, what we call the unconstrained neural networks, the ones that have arbitrary connections. This would be a generalization to the backpropagation. Okay, so something to think about. We will talk about this maybe in the chat. Maybe we'll talk about this on the next lecture. Although the main point of next lecture actually to move away from now this construction to the more of the statistical construction, right? So now we've defined microscopics. Now let's do statistics, statistical mechanics, and thermodynamics. And this is the last slide, which is exactly what I just said, right? So this was the first lecture. It's neural septuples and a unified framework. Here, it was all about dynamics. We ended with this open-ended question of how would you do backpropagation for the unconstrained neural networks. The forward propagation I did here for you, the activation dynamics, but the backpropagation I haven't done for you. So this is your homework. Again, you don't have to submit anything, but you need to think about this. So how would you implement it? What does it mean to backpropagate when you don't have a layered net structure? And then next time, we'll be talking a lot about statistical mechanics and thermodynamics. So things that you do not know about statistical mechanics, you should kind of try to refresh your memory. Like things like generating functions, partition functions, the statistical ensemble, different ones, all this will be covered. And we'll see how those tools are useful to analyze machine learning system. And the main reason for why they're useful is exactly the reason why these tools are useful in physics. The reason we use statistical mechanics and thermodynamics in physics is because we cannot do anything else when the number of molecules becomes more than 10. Well, actually, we fail with three-body problem very often. And here, we will also fail to do any exact calculations when the number of neurons becomes large. And here, we're not even dealing with 10 neurons, it may be 30, 50, 100 million neurons. What do you do with them? How do you analyze the system? How do you study the evolution of the ensembles using the tools of statistical mechanics and thermodynamics? One straightforward generalization from physics would be that all of the usual things apply to the activation dynamics, because you have a state and it evolves. It's just like classical physics. So really, statistical mechanics is the right tool. Now, once you have the second type of dynamics, learning dynamics, then things become much more difficult, and then you will see that very interesting things happen. So, for example, when in the standard statistical mechanics, entropy always grows, and that's kind of because of the activation, the stupidity of the activation dynamics. But once you have a learning dynamics, the opposite things happen, and the entropy can be destroyed, entropy can decay. And so that complexity complicates even the mathematical machinery that we would want to apply. Yet the idea of, yes, let's use as much of this mathematics as we can, because the number of neurons is large, this philosophy will still be relevant. Okay, I ran out of time. Apologize for that, but let's see if there are any questions.
Yeah, there are a few of them.
Mm-hmm.
Can you please return to the slide 15?
Sure.
Can eta be considered as a random value?
Well, that's the assumption here, right? So it's some stochastic noise. Now, nothing is random here because, you know, your computers are deterministic, but things become random. When do things become random from in the system, you know, the dynamical systems approach? When you stop paying attention to details, right? When you start coarse graining, when you have large enough exponents as well, that's when things become random. And so this is, of course, a model, and that's a good enough model for the analysis.
For example, we reached horizontal asymptote U0. Does eta has some probability distribution or just distribution?
Oh yeah, absolutely, yeah. So, but it's more than just probability distribution. It's probability distribution over paths, right? So remember, you know, it's not just P of eta, it's P square brackets of eta of t. So it's probability density functional, not a function. And yeah, I mean, a great question would be, let's model it, right? Let's find this Lagrangian that, you know, just like this one. Where was it? Yeah. Let's model it this way. Sure, of course. But And that's kind of what we'd want to do. And what we do know about it, that it's likely to be non-Gaussian. And non-Gaussian meaning and if it was Gaussian, then it would be just P of eta function. Since it's not Gaussian and you have, moreover, it's not Gaussian, and then it's there are correlations between nearby steps. And so it's a probability density of function that needs to be constructed. Yeah, so very little is known about it. The one thing we do know about this, maybe I should have mentioned that. So you don't often see this noise, but you can reduce it. You can make this noise almost disappear by increasing m, the size of the mini batch, like make it larger, and then eta will be almost no fluctuation. But the problem with this, that you will also make U0 larger. So yeah, you've reduced your fluctuation, there are no fluctuation, but the system doesn't learn as well. So and that's kind of has to do with this, right? How do things depend on m, gamma L plus 1? They're all coupled. They're all, it's not like I can like adjust one and then work with the other. They're all part of the same system, and that's yeah, that's important.
So there may be some connection between the amplitude of eta and U0.
Yeah, through m, for example, and there are a lot more. I mean, they're all connected. Yeah.
And another question: can you please show us slide 13?
Mm-hmm.
So you showed us various modifications of the loss function. The question is, how do we know what is the best modification in our case? How do we know it?
Yeah, so you don't, right? So you every time you develop a theory, how do we know that the standard model Lagrangian is the best to describe high energy physics? We don't. We identify certain principles for which construct the standard model Lagrangian. Those are symmetries. Okay, then we try different terms, and then we do experiments. And then by doing experiments, trying different terms, we see more order, more symmetries. And then they tell us more terms that we can write down. And then people went crazy and say, well, maybe we can predict all the terms in the standard model, and let's write it starting from the string theory, Lagrangian. Yeah, I mean, you can try, but it doesn't mean that it will necessarily work. But the idea is here, you try different things, you learn, identify symmetries, and then use the symmetries to write down certain. So for example, there's a symmetry, permutation symmetry, like all neurons are created equally. So can you use that? All right, and then maybe it makes no sense to write different loss functions for different neurons. Well, because they're all created equally. But maybe the symmetry is broken. And then if it is broken, maybe you can identify and say, well, there's always like 50% neurons that classify and the other 50 that don't classify. Then you've discovered not just symmetry, but also the breaking of symmetry. And then that led you to write the right terms. So yeah, so it's there is a lot. Think about discovering the right loss function, or actually more generally discovering the right septuple. It's like discovering the standard model. They're all the same steps. You know the rules, and now you use and you know the techniques like symmetries, constraints, and then you use them to write something else. And then whatever new result you get, it's something, teaches you something about how we would go about constructing such things next time. Other questions?
Yeah, okay. And is there any difference between minimizing the loss function and maximizing it? For example, if I want to use not the mean squared error, but the reverse 1 over mean squared error.
Oh, absolutely. Well, absolutely. Then you just change the loss function. Let's keep the notation. You always minimize it. So if there is some function that you think you're maximizing, just put a minus sign to it. So you'll always be minimizing. This is a trivial modification. But then you're saying, okay, whether the shape of the loss function will matter. Yeah, it will matter. Now, the one example comes from biology, right? So in biology, what plays the role of the loss function is not the loss function, it's called fitness. Okay, so and then you have, and actually they maximize it. But okay, we put a minus sign, that's trivial, but you don't want to put a minus sign next to the loss function, fitness, but you put a minus sign next to log of fitness. And there is a reason for that. So so here you don't see what's the difference. Do I minimize log or I minimize a function? There's no difference, right? Because log is a monotonic function. However, once you go to statistical mechanics, which is what we're going to discuss next time, there's a huge difference. Okay, what is it that you're minimizing? And then you will see that all those little modifications change your ensemble, and then will change your learning outcome. And yeah.
Okay, thanks.
Other questions?
Can you explain why when we increase the number of batch size, the batch size, then it increases the U0?
Yeah, that's actually, increases U0. Okay. So maybe not U0, maybe I spoke to, maybe it is alpha. I know that as a fact that this combination, U at any particular time has increased. Basically, you are not, that has to do with annealing algorithms, right? So annealing algorithms is an idea that you may have some effective temperature, and then you kind of jump around, and then you gradually decrease your temperature, and then effectively you don't, and because of that you don't get stuck in the local minimum. So I think if you do just the gradient descent without any stochasticity, like M is very large, then effectively you can just stuck in the local minima and never go out of it. There is no like noise to you to where to go, and that will be bad. But extensive study of whether it is U that you're affecting more or alpha, that I don't know, unfortunately. But the possibility of you being stuck because there is no stochasticity, local minima, that's the main problem. Yes.
I have a question.
Go ahead.
So if you increase the number of layers, can you minimize like how non-linear the activation maps are? Like if you have a higher order polynomial, maybe add more layers. So activation.
Okay, yeah, very good. So we'll I'll have a lecture on about what the benefit of the many layers are. Now nonlinearity of F is essential, as we already discussed. Without it, everything just collapses. Now, you're right. Once you have a nonlinearity, then there is a reason for using more and more layers. But I think it's a little bit deeper than that. In a sense that there is some shift to the spectrum of a relevant matrix. Actually, that matrix I can already show you here. So it's this matrix. It has to do with this matrix, but it's something I call the G matrix. It's more of a Laplacian on a graph. And by making the neural network deep, you make certain shift to that spectrum of that matrix that makes the effective number of learnable eigenvectors larger. And you're basically learning in a larger space. And when you make it shallow, you're effectively decreasing the space of possible solutions. And then because of that, learning becomes less of important. And that's a spectral answer to why deep, and I'll give it next lecture, in a few lectures from now, why deep is important, spectral answer. But intuitive, you're absolutely right. So we just said that, having nonlinearity is important because then you can collapse it. And then, the more layers you have, the more kind of the more of nonlinearity you use, right? That's kind of an intuitive question. But I think it has a more precise spectral answer, and that kind of eliminates at least some of the mystery of deep learning, for sure.
I see. My second question is, like, you may have a non-separable function, but when you change basis, it becomes separable. Something like you can have, for example,
that's what I was thinking about, right? Exactly. So then it would be reducible for separate. You're absolutely right. This is the direction. So and then there would be no benefit to having non-separable. Yeah. So if you can just do rotations, right, or something like that.
Yeah.
So to the linear order, I'm sure there is no benefit. You just do rotations of input signals. You can diagonalize it, and there we go. And these rotations can be observed into the matrix before. But maybe there is some nonlinear effect that is beneficial at some place. That I don't know.
Yeah. Right, and also almost all matrices are diagonalizable over the complex numbers. So I was thinking, if non-separable, for example, if you restrict to only polynomial maps where each of the fi of yi are polynomial of degree 2, for example, you can change bases and only work with separable ones.
Yeah, so remember we had the constraints on our f, and so polynomials were not scoring high on that. You really want to output to be bounded, and we wanted to avoid like zero derivatives. We wanted to be linear, and there's and again, this is the whole interesting research area of looking at different activation functions and seeing, you know, what are their benefits, and then we would say, well, I want to investigate the activation dynamics and see what is the role of that. And as you said, playing around with activation functions themselves, with the separability, playing around with all those things, how they affect the learning outcome beyond the linearized level. So the linearized level I will discuss because that's something that can be done analytically. But beyond linearized perturbation theory, there is more to be done numerically as well.
I see. My last question is, do you, before you start training, do you determine the number of times you're going to train your neural network? Because, for example, you may not reach the fixed point and so on, or you may not have an idea.
Right. So for the fixed point, this is for activation dynamics.
Yeah.
So yeah.
Right here.
Yeah. So no, at the end I talked about this right here. So so it's you can do two things. Actually, you can do a number of things. Those are the simplest two things. There are actually much cleverer things than this, what I presented. Some people are in the company are doing exactly that. But this is a trivial thing to do. You say, all right, so I will just do L steps of activation dynamics. And L is fixed. Then I evaluate my loss function, and then I do the backpropagation or whatever I want. How many steps of backpropagation I want, it's up to me. Second step, I do as many steps I needed so that my system converges to the fixed point equation with certain tolerance. This is epsilon. Okay. Then I reach that point. I don't know how many steps going to be, many, fewer. And then after that, you say, all right, now again, I calculate my loss function. And again, I do the backpropagation for as many steps as I want. And that's what I was kind of asking you to do this here. Okay, just to see how that can be done. So really, layerness makes maybe things easier to draw and imagine, but there is no mathematical difference in backpropagating unlayered structure as well.
I see. Thank you.
Sure. Okay. Well, if there are no further questions, I'll stop recording.